is the sum of two other reactions, then the enthalpy change for the overall reaction is going to be the sum of those individual reactions. So if a reaction is a sum of two or more reactions, then the enthalpy change for the overall reaction is simply the sum of the enthalpies of all reactions in the sum. And when using Hess's law, this probably won't make sense right now, but when we go through some examples it will. But when you're using Hess's law, it's helpful to remember these ideas that I've already presented to you. If you double a reaction, then you double the enthalpy for the reaction. Or whatever you scale the reaction by, if you half the reaction, then you're going to half the enthalpy for the reaction. However it's scaled, you scale the enthalpy accordingly. The other thing to remember is if you reverse a reaction, remember what you do here? If you reverse a reaction, you change the sign of the enthalpy. Change the sign of the enthalpy for the reaction. So if you have a positive enthalpy for a reaction and you reverse it, you make the enthalpy negative. If you have a negative enthalpy for a particular reaction and you reverse it, then for the reversed reaction, you make the enthalpy positive. Okay, so we'll just get into this by doing a particular problem. And the problem that I will be working through is on slide 20 of your PowerPoint, the energy PowerPoint. So we're going to use Hess's law to calculate the enthalpy change for the formation of carbon disulfide gas from its elements so in other words, the reaction we're going to be looking at is solid carbon plus 2 sulfur going to CS2. So that's what we want to find the enthalpy change for, and we're going to use the enthalpies for these particular reactions to do so. So we're going to take solid carbon plus oxygen gas going to CO2, and the enthalpy change for that reaction is minus 394, and all of these are going to be in kilojoules per mole. The second reaction is going to be solid sulfur plus oxygen gas going to sulfur dioxide gas, and the enthalpy change for that particular reaction is going to be minus 297, again kilojoules per mole. And then finally the third reaction is going to be the reaction of carbon disulfide gas reacting with 3 moles of oxygen gas, and that's going to be going to carbon dioxide gas and 2 sulfur dioxide gas, and the enthalpy change for that particular reaction is a minus 1104. Negative 1104, again, it's kilojoules per mole. So what we're going to try to do here is we're going to try to make or recover this reaction. We're going to try to make this reaction here. We want the enthalpy for this particular reaction here, and we do not know what that enthalpy is. And we want to find the enthalpy for this reaction using these three reactions here. Okay, here's the way I go about doing this. I look at the reaction that I want, and then I inspect the reactions that I'm giving the enthalpies for. And I check and I say, you know, I need carbon, solid carbon, as a reactant in my overall reaction. Do any of these reactions have solid carbon as a reactant or a product? And of course the first one does. And I notice that the solid carbon in the reaction that I have is listed as a reactant, which matches what I need in my overall equation. And so I leave this particular reaction as it is. The other thing that I notice is I need 1 mole of solid carbon, and in this particular reaction I have 1 mole of solid carbon, so I'm not going to multiply this by anything. I'm not going to change this any way at all. Let's go to this second reaction here, and I'll notice I have some solid sulfur that I need as a reactant, and it is listed as a reactant. So that's good. I'm not going to flip this reaction. I'm going to leave it the way that it is. But I notice that I need 2 solid sulfurs in my overall reaction, whereas I only have 1 in this particular reaction. Because of that, I need to multiply this by 2. But I can't just multiply this by 2. If I multiply this by 2, I've got to do it to the whole equation. Because this ratio holds for everything in this particular second equation. So I'm going to multiply this entire equation by 2. That means I'm going to need 2 solid sulfurs. I'm going to need 2 O2s. I'm going to need 2 SO2s produced. And I'm going to need to multiply my enthalpy change by 2. What's that? 300, that's 600 minus 6, that's 594 if I have that right. 594. Of course it stays negative because I didn't flip it, if that stays correct. What do you think I need to do with this last equation? Inspect what we need, inspect the equation that we have, and then try to figure out what we're going to need here. Well, I'll notice in the product I need a carbon disulfide, and I have that in this particular reaction. That's a good thing. But I'll notice in the reaction that I have the enthalpy for, it's in the wrong spot. I need the carbon disulfide as a product, and here I have it as a reactant. So I'm going to flip this reaction. I'm going to reverse it. Now it's 1 CS2 and 1 CS2, so we're probably okay here. We don't need to do any multiplication of this particular reaction by anything, but I am going to need to reverse this. And if I reverse the reaction, I'm going to need to reverse the sign of this. All right, let's see if I can remember to do this. We're going to have 1 carbon dioxide and 2 sulfur dioxides on this side. When I flip it, these go to the reactant side. And then, of course, these are going to go to the product side. So let's reverse it. Let's see, so we're going to have CO2 gas plus 2 SO2 gas, and that's going to go to carbon disulfide gas and 3 oxygen gas. And because I reversed this reaction, I need to reverse this sign. So I'm going to make this positive. I don't have to worry about multiplying it by anything, because I didn't multiply this equation by anything. Now we're going to add all 3 of these together and see what we get. And if I add all 3 of these together, then I need to add all 3 of these together as well. All right, well, we've got a lot of reactants here. 1, 2, 3, 4, 5, 6 of them. But look, I can combine these. These are all O2s. Anything else I can combine? It doesn't look like it. So my reactants are solid carbon, just one of them, 3 oxygens, O2 gas. I better check to make sure these are the same, so yes, I can add them. I took care of those. 2 solid sulfurs, a CO2 gas, and an SO2 gas, actually 2 of them. And I'm not going to be able to fit this all on one screen, so we're just going to do the arrow here, and this is going to go, I use that, and this is going to go to, let's see my product, carbon dioxide gas, two SO2 gas, a CS2, a carbon disulfide gas, and 3 oxygen gas molecules. Of course, I'm going to need to add all those enthalpies together, so let me do this right quick. So when I add these, of course, I'm going to take this, and when you add a negative, you end up subtracting it. So it's going to be 1104. If I add 594, I'm going to subtract that. Excuse me, if I add a negative 594, of course, I'm going to subtract this value. And if I'm going to add a negative 394, I'm going to subtract that value as well. So I'm going to take 1104 kilojoules per mole. I'm going to subtract 594, and I'm going to subtract 394. And that's a positive 116 kilojoules per mole. Now let's check out this equation and see what we can cancel on both sides and see if maybe we've recovered the original equation that we were looking the enthalpy for. So let's see, I've got a solid carbon on this side, and it doesn't look like I have one on the product side. So this is gonna survive. I have 3 oxygen gas molecules going in as a reactant. And hey, look at that, 3 oxygen gas molecules coming out as a product. Identical in, identical out, we can cancel those. See what else we can find here that we can cancel. Hey look, there's carbon dioxide gas coming out and going in. 2 SO2, uh-oh, did I mess up somewhere? I think I did. Yeah, there's a 2 SO2, I didn't write that up here, there should actually be 2. Notice there's a 2 SO2 here and a 2 SO2 here. So this should cancel this. And what I end up with is solid carbon plus 2 moles of solid sulfur going to carbon disulfide. This is the equation that I wanted. And so because we added these to get this reaction, we add the corresponding enthalpies to get the overall enthalpy of the reaction that we're looking for. Positive 116 kilojoules for every mole. This is how one uses Hess's law. You take the enthalpies of reactions that you know that may be easy to measure, and then you use that information to find the enthalpies of reactions that you don't know the enthalpy for that may be difficult to measure for any particular reason.